So what we want to talk about next is the pH scale, all right? And this is going to be the beginning of tomorrow's note anyway, so we might as well get started on it so we've got kind of like a preliminary of the pH scale, because we have to start getting used to thinking of the hydronium ion concentration in terms of, I'm jumping ahead, but in terms of powers and exponents. So it's good to kind of get a little start on this. So we can put down here a little title here, and actually I'll use black. So we can put a little title here, the pH scale. Nothing special. And then a little note on what the pH scale is. It essentially represents the concentration of H3O+. So the pH scale is a representation of the hydronium ion concentration. All right? It was actually invented by a brewmaster. He was making beer, and he needed a way to represent quickly and efficiently the pH, well, the acidity of the solutions he was creating, of the beer. So he came up with a mathematical scale so that he can easily represent that acidness or baseness of what he was making. So this is a mathematical invention. All right, now I'm going to create the scale. And I'm going to just use a line function here, because I'm going to draw a line across the top, just like you guys have done in the past, and I'm going to create a little pH scale. So you can make your line across there with your ruler, and if we're really picky about the way our picture looks, I'm going to have 14 units that go across, and if you want the 14 units to be exactly the same, you could use your centimeters. So you could mark off 14 centimeters and put your edges. For those of you who are not concerned about the scale being nice and even, you can just put marks semi-wherever, and I'll show you how to do that. And I don't get very excited about it because I'm really not going to measure anything. It's not like it's a ruler. It's just a representation of some numbers. So I'm going to use my line function here, and I'll draw a line here on the end. Look, I can't even draw a straight one. I'll draw a line on this end too, see if I can get it straight. Not bad. And I'm going to just eye it up in the middle, and I'm going to put a line here in the middle. All right. Oh, look at that. That was horrendous. I shifted my line over. Let's see if I can fix it. Oh, I can move it. It's not fun. Okay, there we go. There we got my line in the middle there. And now I'm ready to represent some of our numbers here. And I'll just use a different color pen here. And in the middle, what am I putting in the middle? 7. That's not very exciting. What about at the far end on the right here? 14. So we're on the right end of our scale. And those of you who have designated this in centimeters, it's nice and even. And then over here, I've got 0. Yeah. And I do want a few more marks in here. So I'm going to put in enough marks to get me to 7. So I've got to go 1, 2, 3, 4, 5, 6, 7. Those of you who have used your ruler, you can use your centimeters, but I'm going to just go 1, 2, 3, 4, 5, 6, 7. All right? And I'm going to keep going 8, 9, 10, 11, 12, 13, 14. They're a little fat there at the end, but it's not a big deal. But I do want to have all those steps in there. All right? And I'm going to change my color again. I'll go now to red for, actually no, I want to do some labeling, and we'll label in black again. So up here, oh sorry, in the middle. What am I labeling this guy in the middle? No, I'm not labeling it H2O. It really doesn't have anything to do with water. Nope. I'm labeling it neutral. Very good. Neutral. All right? Neutral. And what am I labeling this side? Basic. Very good. Basic. And I'm going to put strong underneath it. All right? Because I do have weakly basic in this region here, but I just wanted to make sure that we were expressing the extreme. How about on this end? Yeah. Acidic. And I dropped an I here somewhere. Acidic. Again, strong. Strongly acidic. Okay? And that's probably the extent to what you learned in grade 9 and 10. And then you would have done a lot of little experiments and tested this and that, and you would have put it on your scale, and, you know, some teacher would have said, wow, who would have thought that cranberry juice was so acidic? Okay, let's keep going, right? That would have been the extent of it. Now we've got some numbers that we can deal with. What I want you to put now in the row below your pH scale, off to the side here, I want to put square brackets, H3O plus. Okay? So the row underneath now, I'm going to start putting in actual concentrations of the H3O plus. Tomorrow, because I'm not going to get to it today, I'm also going to put another row underneath there for OH minus over on this end so that we can talk about the base part, the OH minus on the other end. So this row here is for H3O plus, and then I'll put an OH minus under it tomorrow. Okay? Now I'm going to add the concentrations. We know that the pH of neutral is 7. But the question is, what's the concentration of H3O plus? Now, there's two interesting things, because you might first think that the concentration of H3O plus at neutral is 0, but that's incorrect. The concentration of H3O plus at 7 is 10 to the exponent negative 7. All right? And these two 7s right here are not a coincidence. Actually, it is this 7 in the exponent that is the pH. Now we've got to learn a little bit about the actual term pH. I'm going to leave some room underneath here, extra line for my OHs. So way down here, I'm going to write an equation for pH. pH. You may have wondered why you always write a little p and then a capital H, right? Well, the capital H stands for H+, which is what we consider our hydronium ion concentrations. The little p, and that's right, I love this lesson because I get to say things like little p and I can giggle. It's fun. That p represents the power or the exponent, the power on the hydrogen ion concentration. So pH stands for the power or exponent that's on the hydronium ion concentration. But you'll notice the power is negative 7. And that's because we really, when we're dealing with acids and bases, we're dealing with pretty small concentrations. We're not dealing with really big numbers. We tend to deal with little numbers. So what this particular brewmaster did, instead of talking in terms of these little tiny numbers, he said, let's remove the exponent off of the power of 10, off of the 10, and let's get rid of the negative. So instead of talking about 10 to the negative 7, let's just say 7. And it's going to represent 10 to the negative 7. So the question now becomes mathematically, how do you take a power off of a number with a base 10? And the answer is you take the logarithm. Have you learned about logarithms in math? So you take the logarithm, which takes the power out, the exponent out, and then you multiply it by -1 to drop the negative. So pH is equal to the negative log of the H3O plus concentration. Again, one of my favorite lessons. I get to say P and log in the same statement. There's fun stuff right there. Yep. Jess doesn't even crack a smile. My potty humor is some of my best humor. All right, what does that do? Like I said, it takes the power off of the 10, and then by multiplying it by -1, it gets rid of it, gets rid of the negative. So a pH of 7 has an H3O plus concentration of 10 to the negative 7. We can extend that all the way along the pH scale. I can go down here to 1, 2, 3, and I can talk about a pH of 3. Well, you tell me, what will the concentration of the H3O plus be? Kristen? 10 to the negative 3. Now notice, 10 to the negative 3 is like 0.0001, right? We're actually getting to bigger and bigger numbers as we head to the acidic side. 10 to the negative 7 is very tiny. 10 to the negative 3 is kind of tiny, but it's less tiny than 10 to the negative 7. So we're actually getting to greater and greater concentrations of H3O plus as we go to the acidic side, and that makes good sense. The more H3O plus we have, the more acidic a substance should be. I can now extend that right to the end, right over here to 0. I'm kind of running out of room, but what should the H3O plus concentration be at a pH of 0? Yeah, Scott, what do you got? Ah, very good. You made the jump. It's 10 to the exponent 0, but anything to the exponent 0 is 1. Scott got that correctly, very nicely. And so this actually has a concentration of 1. I'm going to try to put a nice little 1 here. And it's in moles per liter. If I have a concentration of 1 mole per liter of H3O plus in a solution, 1 mole per liter, then that has a pH of now I'm confused. I'm thinking about the next thing I want to do. That is a pH of 0. That is a pH of 0. I'm thinking what I want to say next, and I'm looking at the clock at the same time. All right? Now, this brings an intriguing thing to our calculation, because we can now head to the base side, and it presents us with an odd situation. Because I can keep going with the analysis, and I think you guys are understanding and buying it. But I can go from 7, 8, 9, 10. I could go up to, say, 11. Let's pick 11 here. And now I can talk about the H3O plus concentration in something that has a pH of 11 or is basic. And I can. Mathematically, there is a little tiny bit of H3O plus even in a base. So H3O plus is always in water, always in an aqueous solution, but how much is there determines the pH. What should be my H3O plus concentration for something that has a pH of 11? Yeah, Kristen? 10 to the negative 11. We're still just extending this idea, and now we're getting to phenomenally tiny numbers. I can extend it right to the end. How much H3O plus will there be at a pH of 14? Really strong base. Yep. 10 to the negative 14. Negative 14. All right? I still have a couple minutes left. I can now maybe do an extension and explain why we have this odd situation. In a different color again, and I'm running out of colors, so I'm going to pick something like blue. Underneath here, I want you to put OH minus concentration, right there off to the side. Now, a moment ago, you probably thought that neutral meant no acid or no base. But I explained to you that actually there is a little bit of H3O plus at a neutral pH 7. It turns out that there's also a little bit of hydroxide in there as well, and it is also 10 to the negative 7. Neutral doesn't mean no acid or no base. Neutral means equal amounts of acid and base. And it's not a lot, but it's a very small amount, all right? And this is a good place to stop, and I'll continue the discussion tomorrow and talk about how we can calculate pHs for some mid-ranges, like what does a pH of 3.75 mean? How much H3O plus is in that? So we'll do some more complicated calculations, but this is a good place to start.